Hello, my name is Rhea McElroy, and this is my Physics 2211 report on Lab 2 over projectile motion. In this lab report, I will go over an introduction, models, the experiment, code, a discussion, and a conclusion. The purpose of this experiment was to observe and analyze the projectile motion of an object and identify the forces acting on it. We did this using the Tracker app, which served as our experimental data, and GlowScript, which we used to create two computational models, one with drag and one without. As a preview of our experiment, we found that drag does, in fact, affect an object as it falls. The main physics principles present in this experiment are the following: Newton's second law, gravitational force, and drag force. Newton's second law yields the equation F equals ma, where F is force, m is mass, and a is acceleration, showing the directly proportional relationship of acceleration to force and the indirectly proportional relationship of acceleration to mass. Gravitational force can be understood through the following equation. Force equals the gravitational constant times the mass of both objects you're observing divided by the distance between the two objects squared. It is an invisible force that shows the attraction between two objects. Drag force is what opposes the motion of an object as it moves through a fluid, otherwise known as air resistance. The following models were used throughout this experiment. The position update formula updates the position of an object where RF equals final position, RI equals initial position, V average equals average velocity, and delta T equals change in time. The velocity update formula updates the velocity of an object, where Vf equals final velocity, Vi equals initial velocity, A equals acceleration, and delta T equals change in time. The average velocity formula finds the average value of the velocity over a period of time, and it uses the final position minus the initial position over the final time minus the initial time to do so. The drag force formula finds the value of the drag force, with B being the drag constant, V squared being the magnitude of the velocity, and V hat being the unit vector of the velocity. We also identified the force of gravity as a vector, where the x position is 0, the y position is negative mg, or mass times gravity, and the z position is 0. We identified the system of our experiment to be the paper ball. The surroundings are the drag force and the gravitational force the ball experiences. To conduct this experiment, we recorded a paper ball being thrown as a projectile with some form of measurement within frame. We then used the Tracker app to find the position in the x and y direction of the paper ball at a particular time. Finally, using the initial conditions given to us by the Tracker app data, we were able to predict what the position of the ball would be with two separate computational models in GlowScript, one with drag and one without. Here are the initial conditions according to both some measurements we conducted and the Tracker app. After weighing the paper ball on a scale, we found the mass to be 0.0045 kilograms. The total time was 0.463 seconds, the change in time / the increments between each frame was 0.03 seconds, and the initial position vector was 4.336 times 10 to the negative 2, 0.9400 meters. In order to find the average velocity, we used the average velocity formula disclosed earlier, and the first two positions recorded by the Tracker app. This yielded the average velocity vector 1.721 negative 0.5660 meters per second. We then plugged these initial conditions into our code in GlowScript. Ball.m is the mass of the paper ball, ball.pos is the initial position vector of the ball, ball.vel is the initial velocity vector of the ball, and delta T is the change in time. We also plugged in some values for the forces the paper ball was experiencing, such as 9.8 meters per second for gravity, and a number for the drag constant found in the drag force formula. B equals 0 in this image because this is the code for the computational model without drag. For our code, we used the time duration t equals 0.463 seconds because this was the final time given to us by the Tracker app. We then calculated the net force of the ball by finding the gravitational force, which we described as the vector 0, negative mg, 0 previously, and the drag force using the same drag force formula we discussed in the model section. Adding these two forces together gave us the net force. Then, using the position and velocity update formula, we managed to predict the position of the ball according to the forces acting on it, whether drag was 0 or not. Because GlowScript has the initial conditions from the Tracker app, we received data that we could then compare to what the Tracker app found. These are the graphs created by GlowScript when the drag constant b is equal to 0. Notice that the x position graph is a straight line while the y position graph is curved. Now, here are what those graphs look like when the drag constant is equal to 0.05. Notice that because of deceleration due to drag, the x position graph is now more curved while the y position graph is a straight line. Here is all the data from both the Tracker app and GlowScript compared to one another. None of them are exactly close, and this is likely due to error, but because the computational model, including drag, is more similar to the data from the Tracker app, we can see that drag does have an effect on the projectile motion of objects. Some mistakes could have occurred from the measurements or calculations that we ourselves took, and is thus due to human error. Furthermore, there are likely other forces acting upon the ball that we did not recognize or include in our calculations. Do any of our models predict terminal velocity? The answer is yes. The y-position graph is excluded because of gravity, which affects the rate of velocity. The x-position graph, however, has constant velocity, so we can use it to predict the terminal velocity. If the object were thrown straight up, would the time this object takes to reach the ground be the same, longer, or shorter than the time it took in your original experiment? We concluded that an object thrown as a projectile would take less time to reach the ground than an object thrown straight into the air. Solving the kinematics equation in the y direction for both of these demonstrates that the number plugged into the, quote, straight up equation would yield a larger number. In conclusion, although the graphs with our data do not perfectly align, they do demonstrate that drag is real, and in creating things such as airplanes or vehicles, it can be important to consider.